Seung-Yeon Ryoo from CALTECH, who will explain us about coarse differentiation and how this helps to analyze embeddings of groups.
I thank the organizers for the opportunity to speak here. So I will start by establishing the notation I'll use throughout the talk. So the definition is that metric space embeds biologically into the bottom space X if following holds, where if there exists a map F from M to X in C1 and C2, such that F of P minus F of Q is bounded by these Lipschitz conditions. The NPM of such C2 over C1 is denoted Cx M, and we will use the notation of Cp of M to be the distortion into OP01 of M. So the basic question you might ask is, when is this quantity finite? When is, let's say, let's ask, when is the distortion into a Euclidean space finite? So in general, this is a hard problem. It's like people have come up with necessary conditions for this to hold, but not many sufficient conditions are known. But we can answer this completely in the category of groups. So a fact is that if you take your M to be the Cayley graph of a group G with generating set S, then we have that the biological distortion of G into some RD is finite for some D if and only if G is finitely generated. And it's virtually a Bayesian. I imagine that many of you would have the tools to prove this with ease, but for the epsilon % of you who don't know of this, I'll give a short proof of this. So one direction is just the Milnor-Spark lemma, because if you have this property, then you have ZD as a finite index subgroup, so it's quasi-isometric to it. And the other direction is that if you had a biological embedding into RD, then in general, if you have a biological embedding into some RD, implies that it is stuffing. Which is defined as a property that for any ball in M, there exists y1 to yk in M such that ball is covered by the balls of half the radius, where k is determined by M itself. You're supposed to take k uniformly over the space. So in particular, if G is doubling, then G is a polynomial growth. Which just means that S to the n is at most a polynomial of n. So by Gromo's theorem on groups of polynomial growth, G emits a finite index subgroup, a nilpotent finite index subgroup. It's called gamma prime. Outside this. So if you take T to be the torsion subgroup of gamma prime and gamma double prime to be gamma prime modded out by T, this is a torsion-free movement group. And by the Mouse-Head embedding theorem, from 49, there exists a nilpotent Lie group I should have just called this gamma, but I just called it this. So G Lie such that gamma double prime is a co-compact lattice in G. So the bilectrous embeddability of gamma transfers through all this process through this because of the Jonas-Fock lemma. They are all quasi-isometric. So this embeds a bilectrous embedding into Rn. And then by Jonas-Fock, there exists a bilectrous embedding of the Lie group into some bigger space R d prime. So invoking results by Hanzu from 83, 89, and an argument by Sems. This should be just Rm for some n. So the result from 83 says that the asymptotic cone of the Lie group is a Carnot group. 89 says that any map from a Carnot group into Rd is differentiable, and the argument by Sems is that a differentiable map is a group homomorphism, so it has to be injective, and hence this should have the Lie group should have trivial center. And now, if you retrace this argument, because gamma double prime is a compact lattice in the Lie group, this implies that gamma double prime is abelian. And by a theorem by Cornelia Violet. From 07, it turns out that gamma is virtually, we call it Z here, virtually abelian. So that proves this fact. I want to mention a conjecture by Cornelia Serra-Ballet. In that same paper, which asks a finitely generated group G embeds elliptically into L2 if and only if G is virtually abelian. So this is a stronger version, this asks for a stronger version of the fact, so this direction is trivial, whereas the opposite direction requires much more work. I don't know how to approach this problem, so I'm saying this to interest some of you if you want to work on a new problem. But my work in this direction is in the following flavor, where I proved in my thesis that if G is a finitely generated and not virtually abelian group of polynomial growth, then there exists an integer D such that the distortion into the ball radius, into RD of the ball radius n gamma grows precisely as square root log n. And this also happens to be the L2 distortion of the ball radius n in the group. So I'll talk about how I came to prove this and some improvements I have made along the way. So here's some general. So
this is for all D high enough?
for
This holds for every D?
this holds for some D. So, but because it holds for L2, it holds for every D prime at least D. So it's like if you draw the graph of the distortion into RD of the ball radius n, it sort of stabilizes as you increase the dimension. So for small d, it's going to be infinite because you can't embed into a line of a large group, but it grows from infinity and goes down and stabilizes to square root log n.
So do you know anything about the L1 distortion?
About the
L1 distortion?
L1 distortion is a fun story. I don't know much, but so.
Sorry, I don't want to say.
So I can tell you that there exists a theorem by my advisor from I think 18 and 20-ish that you know that distortion of the L1 distortion of the ball of radius n in the third Heisenberg group is of order 4th root of log n, whereas the L1 distortion of the ball radius n in h 2k plus 1 is on the order of square root log n for k at least 2. If you want to know the LP distortion, it holds that the LP distortion, I computed in my thesis that this is on the order of log n to 1 over maximum p2 with a constant depending on p for p between 1 and infinity. But L1 distortion is a much harder story because you need to work on isoperimetry inequalities in such groups, and those are hard to prove. Any more questions? So I'll talk about some generalities about embeddings and metric spaces. So in general, we don't have a clean condition for bi-Lipschitz embeddability into Rn, but I'll present the candidate such statement. So the question is to characterize the metric spaces embed bi-Lipschitz into some Rn. And one necessary condition I mentioned here is that it has to be doubling. So a necessary condition one is that n is doubling. A second condition is that n should embed bi-Lipschitz into L2. So this might sound like a useless thing to require because it's like if you embed into Rn, you can embed into L2, obviously, but there is a characterization that a metric space embeds with distortion d into L2 if and only if for any n and for any symmetric n by n matrix that is positive and whose rows sums to 0, we have that for every x1 through xn in M. The following inequality holds, where if we compare the two quantities, this thing looking like a positive form, the right-hand side is obviously bigger because you took absolute values, but it states that it's less than by a multiplicative factor of this given here. And this result is due to lineal London and lineal London and Rabinovich in 95. in practice, this is hard to verify because we can't use this effectively against like groups, for example. So, but this is seen as a way of characterizing embeddability into L2. So, question by Long and Plow is that are these sufficient? So, are these sufficient? Or an equivalent way of saying this is like this: every doubling subset of O2 embed maliciously into Rn. So a partial result towards the Long-Plow question is given in the following form. So a theorem by a Smollett states the following. So it states that if M is a k-tupling metric space, then for any epsilon small enough, there exists a map f sub epsilon from M into R of dimension a constant depending on k over epsilon, such that f epsilon of p minus f epsilon q is bounded above and below by not the first conditions, but these bipolar conditions. Which more succinctly written can be written as like C into R of dimension dk over epsilon of n even minus epsilon is at most this. So one corollary is that from this is that you can see one direction of this inequality where a corollary of this is that the L2 distortion of the ball radius n in gamma is at most square root log n. This is because this is going to be equivalent to C2 of Bn gamma with distance raised to 1 minus epsilon taken to be 1 over log n, and this is going to be at most square root whatever square root epsilon, which is square root log n. So you might ask if we can come up with improvements to the Smollett embedding theorem and what that would imply for embeddings of groups. So a theorem states that the following two facts about the sharpness of the Smollett embedding theorem. So one is that the factor 1 over square root epsilon is necessary Heisenberg group. And the second fact is that if you're willing to sacrifice the distortion a bit, you can get the following. So you can embed into a Euclidean space of dimension log k of this outer embedding with distortion behaving like this. So I'm going to add an extra factor of delta here and raise this to 1 plus delta and divide this by delta here. So you can see that the distortion is sharp in the slot embedding theorem, but the dimension is not. So a question that we can ask is, can we take the dimension to be a fixed integer depending only on the doubling constant, while we maintain the sharpest distortion? Because if this were true, then it would imply that the distortion into if this were true, then this would imply the upper bound for the distortion into RD. And the result is that it was first proven for the Heisenberg group that this has an affirmative answer. And what I've proven in my thesis was that this also holds for groups of polynomial growth. And for nilpotent A groups. So yes, I can give them any sub-Riemannian distance and it will hold for that. So a corollary of this is that there exists a D such that CRD of the Bn gamma is at most square root log n. So that's how I got the upper bound for these quantities here. So after this result, I've been trying to extend this type of result to different sort of spaces. And what I found is that one sufficient condition for that to hold is if we have good heat kernel estimates. I'll label this section the slot embeddings. So I've been trying to prove this in the affirmative for the past 2 years, and what I've stumbled upon is the following. So when you want to prove a statement like that, you can make some modifications to your space. So it's enough to prove it for finite doubling spaces because you can take a net in the space and use an approximation argument. And then if you have a finite doubling metric space, there is a construction that you can transform it into a graph that has a measure that is doubling and satisfies a one-Poincare inequality. So a result by Jorn and Seung-Yeon is that a compact doubling metric space, it embeds as a boundary of some better behaved doubling metric measure space, and biologically embeds into a compact doubling metric measure space it's actually given as a graph, given as an infinite graph. With a one-Poincare inequality. So it states that for any function you have the following inequality where if you average a function on a ball and you take the difference of its average, the L1 difference, it's bounded by this integral on a slightly bigger ball of the gradient of f. And a result by Kanai 85 states that we can replace the space with a manifold with the doubling and one-Poincare inequality. So for the purposes of proving, for the purposes of answering this question affirmatively, it is enough to assume that the space is a doubling Riemannian manifold with a doubling measure that satisfies a one-Poincare inequality. And if you have this, there's a result by Gorian from 91 and Zilov-Kost 92 that states that in this case the heat kernel is very well behaved. So you have that is equivalent to, and the heat kernel is equivalent to the volume of the ball radius square t around x times the exponential of this Gaussian term. So what I have is that if, in addition, we have the stronger heat kernel estimates of the following. where you have the gradient and the Hessian being bounded by this same quantity, then M emits a sharp, a small embedding. And the reason this is useful is that it has as example. So, for example, nilpotent Lie groups satisfy this heat kernel estimate. So I have a easier proof of this fact that I prove in a somewhat like more contrived way. But in general, if you want to get heat kernel estimates, especially on the Hessian, you need rather strong assumptions on the space, because you at least need sectional curvature bounds, and even that is not enough to prove. That doesn't seem to be enough to prove those estimates. So I've been trying to come up with workarounds to that estimate, and now comes the topic of coarse differentiation. And what I realize is that what I'm really doing here is that I'm coarsely differentiating well-behaved functions on the space. So an upcoming theorem with Hyun-Chul Jang and itself is the following. I should have mentioned his name in the title page, but so the theorem states the following. So if you assume that M is a doubling manifold, and let's say it has a two-Poincare inequality. So if the manifold satisfies the following two conditions, then we can prove a sharp Oswald embedding. So the first states that we can solve Poisson equations on the manifold in a nice way. So if we can solve the Poisson equation, nicely, the following sense, where if for any ball in the manifold, the manifold, and any function that is L infinity on a ball, the solution to the following Poisson equation this should satisfy that the gradient of U, infinity norm, is bounded above by R squared times just R of F L infinity norm. So this holds true if your manifold has non-negative Ricci curvature, and also if it's alpha is regular and has a low Ricci curvature bound. So for reference, there's a result by Biroli and Moscow from 1995 that states that you automatically have the L infinity norm of VR bounded by R squared times F L infinity norm. So what I'm requiring is a stronger condition on the control of the gradient of the function. And the second condition that we impose on the space is the following. So you want to say that for any ball in the space, there exists functions f1 to fn on this space such that we have the following coarse differentiation statement. So for any one-Lipschitz harmonic function G from a bigger ball into R with A is 2, there exist numbers alpha 1 through alpha n such that the gradient of G minus some alpha I fi infinity of B BR is bounded above by 1 over R times A to the minus C. So far we're able to show that if your manifold is a has non-negative Ritchie curvature, then this holds and this holds where these depend on your choice of A. We haven't been able to show that this is independent of the choice of A, which is stopping us from proving the Sharp-Swat theorem for non-negative Ritchie curvature manifolds. And I should state the rest of the theorem. So then it's a Sharp-Swat embedding. So that's the type of coarse differentiation I was mentioning about embeddings, making embeddings into Rn. Yes?
Is there a toy example where the answer is not known other than space?
A toy example where this is not known?
Where is that?
Non-negative Ritchie curvature manifolds. It's true that it holds in this case, that this holds, but we haven't been able to show it for this yet. So the way we've been trying to do this is that this is motivated by the fact that by two facts. So maybe I'll risk using this word. So there's the Rademacher and Shiger differentiation theory. That says that this holds for R very small. So it states that the classical Rademacher theorem states that you can differentiate any function at very small scales and get this type of statement. And the Shiger theorem states that this holds when your space is doubling and has a one-Poincare inequality. And if you take R to infinity, this is just the finite dimensionality of harmonic functions of a certain quantum growth rate. So the linear case is by Lee and Tam, and the general growth rate is by Goldman and Causey. So we've been trying to make their proof make a stable version of their proof to prove part 2 there, and what we've been able to observe is that the restriction map from this bigger ball into the smaller ball is a Hilbert-Schmidt operator. So it's close to being close to having finite dimensional image, but the issue is that we can't control the range of such a map for various different A's here. I'll close this off by stating how coarse differentiation can be used for proving lower bounds of embeddings to show that something doesn't embed very well. So I'll state this in the case of Carnot groups. So if you let G be a Carnot group, and F is an L2 function, such that its gradient is in L2 of G, then we have the following statement where you can compute the L2 norm of the gradient of F with the following quantity, where you integrate over G, and you integrate over all scales of the so-called beta numbers. dr over r cubed and dx. Where this beta number is defined as the infimum over all affine maps A of the average over the ball radius r of x of f minus a squared 1 over 2. So this was proven for Rn by Doran-Searle in 85, I think, and for the Heisenberg group it was proven by Fassler. I want to end this by stating one last extension of the above theorem, where I proved last night the following theorem, where if you have M be doubling two Poincare inequality manifold, you have that the integral over M of the integral over all scales of the beta numbers at Vr of x, Vr over r cubed, x over 2 is bounded above by gradient of L2 of n, where the beta numbers are now defined as follows. So we don't have affine functions on manifolds. So we instead use the infimum over harmonic functions on some bigger ball of the difference over the ball of this quantity. And I suspect this type of results can be used to prove non-embeddings of different spaces and possibly give a way to compute the outer distortion of various spaces. So I'll end my talk there.
Questions?
Yes.
Say one thing on how you deduce probability result from your theorem for
So the way you deduce a non-embeddability from this type of result is that you look at, so here the affine directions mean the horizontal directions. So if you consider variations of your function on vertical directions, then these affine functions cannot read those directions. So you can prove an inequality that states that some singular integral measuring the variations along the vertical directions is bounded, which gives you the non-embeddability result.
Also the estimate for the distortion.
Yes, that it gives you precisely square log n.
I have one question. What replaces affine functions in the case of Carnot groups?
In the case of Carnot groups, by affine I meant the horizontal functions. So if you want to measure the L2 of the gradient, you can use the horizontal functions. If you want to measure higher fractional Laplacians, then you have to use homogeneous polynomials of a certain degree.
Thank you.
So, in your theorem that you raised unfortunately, where you said that no, it was a question. It was about embedding into L2. Yeah, your question whether it was still open, whether the two necessary conditions were not sufficient for embedding into Rn. So one of them was to have a biluminescence embedding into L2, and the other one was to do BW. So what about if you replace the embedding into L2 into LP? Do you know if it's also open, or whether you have there are other examples?
There are examples, I think there are examples by Laforgue and Nauer, where they construct doublings of LP for P bigger than 2 that don't embed into Rn. So it really is an L2 phenomenon.
Okay. Thanks.
If there are no other questions, let's thank Seung-Yeon again.